Hi, it's Mr. Johnson. If you are watching this video and only this one, I want to say that it's been a long time since I've seen you, and I hope you're doing well. If you do have questions about how pedigrees are put together, please watch the first video that I showed or rewatch one of those two ed puzzles that I shared at the beginning. The goal of this video is to sort of help you not put pedigrees together, but rather to interpret them. So again, if you need to know how to put the pedigrees together, how to make them, please go to the previous video. So let's start off with analyzing pedigrees by looking at the one below. I've given you a little bit of background information to ease us into this whole process. It says the family tree below shows the trait of having attached earlobes. So I can underline that right there. We're talking about attached earlobes. Now, having free earlobes is dominant. So what I can do is I can put capital F and I can say free. I know that right now. However, people with attached earlobes are shaded in. And so we know that little f is attached and it's shaded. So we'll remember that anything that's shaded is attached. Okay, so let's answer some of these questions over on the right. Let's describe the sex and characteristics of person labeled A. So let's take a look. Person labeled A. I'll remind you that in pedigrees, the generations are on the left, and normally we would have person lined underneath. So this would be 1, 2, this would be, and then we restart 1, 2, 3, 4, restart 1, 2, 3. So now we can just talk about number of people, because pretty soon we are going to try to label everyone we can on this pedigree. So let's go back up. What is the sex and characteristics of person labeled A? If you said the sex is male, you are right. Male, because males are squares. What about the characteristics? Well, they're shaded in, right? So we can look over here at our key and we see that shaded, right? This right here is attached based on what we've been told. And so this is attached earlobes. Attached. I know that's bad. It's actually worse handwriting than I have on the whiteboard. So I apologize. But that says attached there. Okay, so describe the genotype of person labeled B. So this is where things get a little interesting. So we see this first question is actually not too bad. Person labeled B. Well, we see that they're shaded in. And if they're shaded in, based on what we just talked about there, shaded means that they have the recessive trait. So we know right away that they are little f, little f. Okay, so little f, little f. I think I'm going to try and write over the top like that. Okay, so anyway, from there, we can label a few other ones too. So we could label, we know that that's little f there. Describe the person, this next question, describe the genotype of the person labeled C. Well, person labeled C is generation 2, person 3. So we call them 2, 3. So 2, 3. First of all, let's back up just a little bit. Based on the fact that we know, because we were told back up in the problem, right? Free earlobes are dominant right there. Because we know that, then that means that anyone that's shaded in is the recessive trait, which is attached. And so person 1, 2, person 1, 1, letter A, that person also is shaded in, so they also have little f, little f. And so the nice thing is if I tell you that it's recessive right away, you can just go ahead and shade in, or you can just go in and fill in all of the genotypes for anybody that's shaded. So that makes it pretty easy. But this is asking person labeled C right there. Okay, so person C is 2, 3. We know that 2, 3 got one of their alleles from this person, from their dad, and their dad had to give a little f. But if we look at them, their characteristic is unshaded, and unshaded is free. And so we know that the other individual or the other allele that they have to have is that big F allele to give them the dominant trait. Now we could have figured that out anyway though. And the reason we could figure that out anyway is if we look up at person 1, 1, again, 1, 1 is this person right here, they have a little f, which is how we know that that person has to have a little f. But let's look at 1, 2, this person. We know that they are unshaded, they're empty. So we know that they have to have a big F for sure. So since person 2, 3 has the unshaded box also, they got the big F from their mom, and they had to get the little F from their dad. And this is where my drawings are maybe going to get a little messy. Nope, no, I don't want that. Do green. Sorry, colorblind folks out there. Okay, so I know my screen's getting a little messy, and I'm going to clean it up in just a minute. But point is that person 2, 3 got the big F from mom and the little f from dad. I'll erase some of this business right here, get rid of some of my lines. All right, clean up the screen a little bit for you. Okay, now if we come down to this next person, fix my numbers there. If we come back down to person 2, 1, right here, person 2, 1, well, they got one gene from dad, 1, 1, and one gene from mom, person 1, 2. So they for sure from dad, they had to get that little f. And they're unshaded, right? They're not shaded, and based on our key, we know that that would mean that they have the dominant trait. So they had to get that capital F from mom. Now we're almost there. We're almost done with everybody. So if we keep coming down to the bottom, we answered the question. Sorry, we answered the question a long time ago. We answered it. Person labeled C, 2-3, person 2, 3, they're big F, little f. Could a person labeled D have a recessive allele? Could that person have a recessive allele? I'll give you a second to answer. What? I can't hear you. Oh, is the answer yes? You are right. So it could have a recessive allele. And the reason that they have a recessive allele, we know since they are unshaded that they had to get that capital F, and they had to get it from their dad. Mom also gave an allele, and the only one that mom could give was a little f. So we know that person labeled D is big F, little f. So that's just a little introduction about how to analyze pedigrees. So here are some general rules that we might be able to use. And again, please take notes. This is going to be very helpful to analyze pedigrees. If you need to pause this video to go get it, you can. A few things. First of all, recessive traits tend to be rare. They tend not to show up very much. Also, they can skip generations. What do I mean by that? Well, this right here is going to help us understand the most important way to identify a recessive pedigree. If we come down here, let's look at this left pedigree here. Let's look at this one right here. So that left pedigree, if we look at it, we have parents, and I'll number them so we can tell. Here's generation 1 and generation 2, person 1, 2, person 1, 2, 3. Okay, so now we can analyze this. If we look at generation 1, 1 and person 1, 2, well, they don't have the trait, but they have this child here, 2, 2, that does have the trait. So let's point out what can't happen. If the shaded in was dominant, then they have to have at least one dominant parent. I'll say that again. If, and again, this is not true, but if 2, 2 were dominant, they would have to have at least one dominant allele. If we look up at the parents, 2 or 1 1 and 1 2, do you see how neither of them are shaded in, but the child is shaded in? Well, let me show you why this is a recessive gene. If we had, oops, I'm using different letters all of a sudden. If we had big or little r, essentially times little r, can we possibly get big R, little r, or big R, big R? Well, no, neither of these have a big R to give, and so that's impossible. And so we can't have two parents that look the same as each other have a child without the trait unless that trait that we're tracking is recessive. Can we have dominant look and a dominant look have a kid that's recessive? Well, yeah, that works. That's how we have traits skip a generation. And the reason I'm able to write these parents in is because of the very fact that they have a kid that doesn't have the same characteristic as them for the trait we're tracking. So here is the key right here. Two parents with the trait can't have a child without the trait. That right there is really important. Right there. I'm making all sorts of fun yellow arrows at it because that's really, really important. So anytime we're analyzing a pedigree, the very first thing that I look for is I scan and I look. Do we have somebody with the trait? Do we have somebody with the trait that has two normal parents like we have down here in our pedigree on the left? If we do, if we have someone who has the trait with two normal parents, we know that it has to be a recessive trait we're tracking. And we can see that down here in the pedigree on the right too. Again, we have two parents that don't have the trait and the child does. The only way that can happen is if those two original parents were carriers for the trait, if they carried it but didn't show it. Okay. Now let's go to some examples of pedigrees or of traits that are recessive that can be passed on. So most human disorders are recessive. Most human genetic disorders are recessive, and they can vary in how risky they are to somebody's life. People with the recessive disorder, again, they are born from heterozygous parents that don't have the disease but carry the gene, and again, we call them carriers. A few examples are listed. Tay-Sachs. Tay-Sachs is one where the child will be born, but unfortunately their nervous system doesn't work correctly, and they usually die within the first couple of years of life, which is very sad. And it's a genetic disorder, but you know it's something that that can be tested for now. But regardless, it is a recessive disorder. I'll jump down here to some of the other examples that are sort of unique. Albinism. Albino means that they don't produce melanin. Melanin is that pigment that protects your cells from having mutations happen in their DNA. And so somebody with more melanin blocks more of that UV rays, and they tend to be darker, but they tend to have kind of less instances of skin cancer. Somebody who has albino does not make any of that melanin. We can kind of ignore our right side. So if we look down at being an albino, what we see is that people who do have the trait, people that are albino, they have, this person and that person and that person. They all have the same parents who do not have the trait of albinism. So that is a recessive characteristic. And that's a nice thing about these pedigrees is we have to do kind of unique testing to people who do have certain traits. And before humans had the ability to analyze the very DNA itself, pedigrees were really, really useful. But we'll talk about that technology later. Another thing is cystic fibrosis. So cystic fibrosis is, if we look at these two pictures on the top, these two pictures are sort of showing the tubes that